Today we're going to do the notes for Unit 1, Lesson 2 on scientific investigations. This is going to go through the different types of variables, different parts of an experiment, and the scientific method. Some types of scientific investigations can include experiments. We all know that an experiment is a kind of test that a scientist will run under controlled conditions so they can make predictions of their outcomes and then see if their predictions were correct at the end. Scientists can also use observations to study, to make investigations, and models. Models are super helpful for things that are either too large to study easily or too small to study easily. An example of something that would be too large to study would be the solar system. Okay, so it's very difficult to actually go out and see and fathom how far Mercury is away from the sun or how far Pluto is away from the sun, versus looking at a model and being able to see it on a smaller scale. Another example of something that would be too small to study would be like an atom or a cell. Okay. Yes, under specific conditions and with certain tools, we might be able to see them, but it's much, much easier to see the different parts of an atom or the different parts of a cell if you have a model of it in front of you. Just kind of helps you visualize it a little bit better. Some parts of scientific investigations. First of all, we have the hypothesis. We all know a hypothesis is that, like, what am I going to test? What's my testable idea or explanation that can eventually become a scientific investigation? We always word our hypotheses in 8th grade science as if, then, because. If I do this, then this is going to happen because this is why I think that. Okay, so give me a reason why you think your if and then makes sense, right? Your hypothesis has to be backed up by some kind of a reasoning for thinking what you're thinking and some kind of reasoning for predicting your outcome of your experiment. Remember, just as a side note, when you see highlighted words here, those are your vocab words. So you want to make sure you go to the top of your notes and fill out your vocab words. Prediction. A prediction is exactly like it says here. Okay, so prediction is based on prior knowledge, and it also is based on your observations and your reasoning. So it's kind of similar to a hypothesis, except it's a little bit less structured, and it doesn't necessarily have to lead to a test. We also have a couple of different factors called variables. We have independent and dependent variables. The independent variable is the variable that's actually being tested. I like to remember this as independent, I change it. Okay, so independent starts with the letter I, and I, as the scientist, am in charge of changing this variable. So this is the factor that the scientist is actually changing or adjusting or testing in an experiment. Remember, these highlighted words that you see here, those are your vocab words. And I'm not going to walk you through the vocab this time, so it's your responsibility to go to the top of your notes and fill out your vocab as we go. In an experiment, something that's also very important to remember is that there's only one independent variable in any good investigation. You only want to change one thing at a time so that you know that that's the only thing that's affecting your investigation. Keep that in mind. Another part of a scientific investigation is your dependent variable. So I like to remember it as dependent gives you data. Dependent variable is the factor that you measure. Okay, or this is a little bit wordy on the slide here. It says the factor that changes as a result of adjusting the independent variable. This is the factor that you're measuring. This is where you're getting your data. How do I know that my independent variable made a difference in my test? Well, I'm going to measure my dependent variable. I'm going to take my data. So dependent starts with D, and so does data. Dependent variable gives you data. Okay, so again, this is the factor that is measured. You're going to collect observations and data. So record all of your observations and data in an organized way, like a data table, and then you can take that information and put it into a visual representation like a graph. Okay. There's two different types of observations that our book does not get into, but it is very important. And these are two of your vocab words. qualitative observations and quantitative observations. Qualitative, you can see hidden inside that word is the word quality. Okay, and quantitative, you can see hidden inside that word is the word quantity. Okay, so qualitative is qualities and quantitative is quantities. So what does that mean? So a quality of something is a characteristic or a description of it. So qualitative observations are going to be those observations that you can take that just describe what's happening. They describe the object, describe the substance, describe the test. But a quantitative observation is more the opposite. That one is going to give you a quantity, which is a number, okay? Examples of qualitative observations or qualities would be anything that you can observe with your five senses, things like color, odor, texture, sound, taste, anything that you can describe using your senses. So again, we can just give a couple of examples. If you are observing a liquid and you see that it's green, that's going to be a qualitative observation. So anytime you're observing color, qualitative. If you are observing taste of something, that's going to be a descriptive way to describe that or a descriptive way to observe that. And so if you say the candy tastes sour, that is a qualitative observation. The blanket is soft. That's describing the texture, okay? So again, qualitative observations describe qualities. Quantitative observations are going to give you numbers. So that's going to be more of a measurement. So a number with a label that describes something. Could be anything from like size to mass, temperature, time. Any time that you can use a number to actually quantify or give a number to that observation, that's quantitative observation. Examples of these are the hallway is 12 meters long, okay? My quantitative observation is 12 meters. It's my number, 12, and my label, meters. That make it a quantitative observation. The wood block has a mass of 20 grams, okay? 20 is my number, my unit is grams, and mass is definitely a way to quantify the size of that wood block. Lunch, like the lunch period that you guys get to eat every day, lunch is 27 minutes long, okay? 27 is my number, minutes are my unit, and that's a length of time. It is a way to quantify lunch, okay? So again, remember, quantitative observations give you a quantity. That's a number. So you have a table in your notes that I want you to take a minute to fill out. You can search for an image on Google and insert it into your notes so you can get a little bit creative with it. But you are going to find an image of your favorite animal or an animal that you like or an animal that you want to observe. And then I want you in that box, in that little table, to make 2 qualitative observations and 2 quantitative observations. Okay, you can pause this video and do that on your own. When you're done with that, we're going to move on. So what are some scientific methods? So some ways that scientists actually go through their tests. It's important to remember that there's not necessarily one way to go through the scientific method. You can kind of repeat steps or loop through steps over and over again, depending on what's going on with your test, depending on the data that you get. But the very first thing you need to do is figure out, what are you testing? What's the problem? What are you trying to figure out? So define your problem. After that, you're going to form your hypothesis. That's your if, then, because statement. And you're going to make those predictions. This is what I think is going to happen. If I run my test, this is what I think is going to happen. After you form your hypothesis, then you got to figure out, okay, how can I actually run my test? This is where you need to get really specific. So plan your investigation. Think of this part as kind of like writing a recipe. You want to plan an investigation so specific that somebody else could read through your procedures and do your experiment exactly the way that you did it. Just like I said, reading a recipe. The best recipes are the ones that are easiest to follow and you know exactly what to do. You need to identify your variables. Figure out, what am I supposed to be testing? What's my independent variable here? And then how am I going to measure that? How am I taking my data? That's your dependent variable. Collect your data in an organized way, so usually using like a data table. And then after that, you can turn all of your data. So after you're done running your experiment, you can turn your data into a more visual representation by putting it into a graph. Okay, we'll cover graphs in 1.3, but this is where you're going to actually be able to visualize your data and interpret it a little bit easier for better analysis. After that, you can draw your conclusions. Was my hypothesis correct? Was it not correct, or was it supported or not supported? Do I need to retest? Did something go wrong in my experiment? Did I make a mistake? Anything like that. All of that will happen in your conclusion. And again, just remember, you can always, if you notice something goes wrong or isn't going the way that you thought it would, and you think, I should have done this a little bit differently, you can always back up and then go through the steps again. Okay, it's kind of a loop. You can always keep going back through. Predictions and inferences. These are sometimes kind of difficult to tell the difference between, but a prediction shows what you think is going to happen in the future because of what you see now. Okay, so a prediction shows cause and effect based on logic and prior knowledge. So you can predict if it's raining outside in the morning on your way into the school, you can make a prediction that the hallways might be a little bit slippery and you might see some of your classmates fall down in the hallway on the way in. Okay, if we're not careful. That's a prediction. Okay, I see that it's raining. I know everybody is going to be walking in with wet shoes. And based on my prior knowledge, I've seen it happen before. Our hallways, our floors are all waxed, so they can get a little bit slippery when wet. I know that this is happening. So I'm going to make a prediction that I'm going to see some people fall down on my way into the building today. Okay. An inference, which is another vocab word, an inference is a little bit different. An inference, I like to think of it as an assumption. This is an explanation of what's going on based on what you already know. So let's say you walk into class and Mrs. Rinear, I'm standing there in the front of the room, and I start class by saying, like, all right, guys, get your books out. We're just going to get these notes done. Okay. If that's my attitude when you walk in my classroom, you can make an inference that maybe I'm not in a great mood, and maybe something's going on outside of class that's making me not happy. Okay. Because if that's how I'm starting class, you can make an inference that Rinear's not in a great mood. And then you can kind of judge your behavior or plan your behavior according to that, right? You're just making an assumption based on what you observe. You know, if I'm standing there not very energetic and I'm being real short with you, I'm not greeting you and, you know, excited to see you, I'm not acting all happy to see you, then you can make an inference that I'm not in a great mood, even though I don't necessarily tell you, hey guys, I'm in a really bad mood. Let's get these notes done. But that's an inference that you can make based off of my personality and how I'm behaving. So how do scientists form conclusions? Scientists can form conclusions by looking at the data that they collect. So analyzing their dependent variable, looking at that data table and that graph, and then see, does my data support my hypothesis? If it does, then great. If it doesn't, then what do I need to do a little bit differently? How do I need to go back and retest or reanalyze or replan my whole investigation? So interpret that data and use my logical reasoning. What do I need to do from there? Okay. Inferences and conclusions are very closely related. They work together. So inferences, those assumptions that you can make based on what you see and what you observe, those can lead to further investigation. Okay. So those inferences that you see happening throughout your test and those assumptions that you're making, hey, I saw this happening and I think it might have been because of this. Okay. That inference can lead to a whole new test or a whole new valid conclusion. So inferences and conclusions can go hand in hand. Scientific methods are used in some different ways because different situations require different methods. If a hypothesis, if you go through your whole test and you decide that, you know what, my hypothesis was totally wrong and my data did not support it and I was way off base, that doesn't mean your experiment failed. That just means that you learned something. Okay. Even if your hypothesis isn't supported, it's still useful. I think it was Alexander Graham Bell that said he learned, 100 ways to not make a telephone before he made one that worked. Maybe it was Thomas Edison about the light bulb, but regardless, every time he ran a test, he realized, okay, well, that didn't work. So that's helpful to know not to do that the next time. Okay, there's often a lot of cycles of testing, data analysis, retesting, more data analysis, retesting again, more data analysis before you can get to a hypothesis that's actually supported. Just think about all the steps that scientists are going through right now to try to find a viable vaccine for COVID. This is all just cycles and cycles and cycles of testing, learning new information, testing and learning new information. So what makes a good scientific investigation? First of all, you have to be able to repeat and replicate your results. Repetition is if you can do your experiment many, many times and get the same result each time, or very, very similar results. So that's repetition. Can you repeat your experiment? Replication is having somebody else do your experiment and getting the same results. And I always like to think of this as like cooking with a recipe, okay? Repetition is like if you have a recipe that you're really good at and you can make it over and over again and it comes out tasting the same every single time, then that's repetition. Replication is what happens when you try to follow somebody else's recipe and you try to make it taste exactly like theirs. I always like to think of, my mom, she's a very, very good cook, but she never writes down her recipes. She just happens to remember it in her head. So if I ever try to replicate one of her experiments, it's so difficult because her recipes are so hard to follow because she just has it all in her head. So trying to make her recipes are very, very difficult to replicate. And it never comes out tasting the same. So where can I find reliable scientific information? If I'm trying to do some research, to plan a test, to see what's going on here, to plan my investigation, where can I actually find that reliable information? Well, you don't just want to go straight to Google and type in, the title of your experiment and get your information that way, because anybody on the internet can post anything to the internet and it may or may not be reliable. Some of the most reliable information is from peer-reviewed scientific journals. Okay, so if you're ever looking for information on how valid a test is or how true something is, the first place you want to go is to a peer-reviewed scientific journal. That means that a scientist did a bunch of tests, repeated them, had other people do them, so they were replicable. They could replicate them. They were replicable. And then they published their journal. They published all of their data. And then other scientists all over the world reviewed the information and said, yes, you're good to go. This is valid. So for something to be considered peer-reviewed, it has to go through a ton of steps. So peer-reviewed journals are your number one most reliable scientific information that you can find. Other places that you can go are sometimes internet sources like government and academic web pages. But even then, some of these government and academic web pages can be published by students or they can be biased, is what I want to say here. Okay, so these are just some examples of some of the peer-reviewed scientific journals that are a little bit easier for the normal average person like you and I to read. And they're out there. Sometimes scientific journals are full of like really complicated language and really tough to read. But then if you look at these peer-reviewed magazines, sometimes they put it into language that makes it easier for the normal person to understand. All right. All right. Well, that's the 1.2 notes. Next up, we have 1.3.